Good morning. My name is Lita Lidyawati, and I'll be one of the presenters today. I'm responsible for explaining our research as the requirement of the IJEECS journal. Joining me today are my esteemed colleagues, Pak Sabat, Anwari, and Ibu Dini, Fauziah. Okay, here's what you can expect from our research. Our research title is Challenges of Implementing Protection Systems in Smart Grids, a review. From Department of Electrical Engineering, Institut Teknologi Nasional, Bandung. For the first section is the introduction. The smart grid is a revolution in the conventional power grid by adding bidirectional electricity and information, supported by the development of artificial intelligence in both equipment and control systems. The main goal of a smart grid is to optimize production, transmission, and consumption from distributed and varied power sources. One of the most important aspects in the fields of smart grids is self-healing. Self-healing capability has two basic properties. First, detecting when the grid is not functioning properly, and second, carrying out restoration actions so the grid functions normally without any human intervention. With smart grid self-healing capability, the electricity network has high performance, including reduced downtime and increased reliability. This survey paper presents research on self-healing capability and discusses challenges associated with different methods used to fulfill its functions in order to identify the most effective and efficient techniques. The novelty and related contribution of the review paper are threefold. First, based on the results of the survey and discussion, a comprehensive picture of the direction of development of the protection system in smart grid is presented. Second, various review papers have concluded that the self-healing capability of the smart grids is interesting for further research. In the discussion, the author proposes a systematic procedure to obtain an effective algorithm. And third, based on a review of several papers, the results highlights numerous challenges for further research. The second section is the protection issues in the smart grid. This is the illustration of a smart grid. There are comprises into some diagram blocks. First, energy service provider, distribution control center, transmission control center, distribution power electronics, distribution substation, transmission substation, and power generator. And this is the main features of a smart grid. Storage options, power quality, energy efficiency, demand response, electricity market, self-healing, and energy generation. Self-healing itself is a capability that allows the electricity network to reconfigure itself or automatically restore to normal operating conditions when a fault occurs, ensuring the uninterrupted flow of electricity. The self-healing grid can be explained simply as an intelligent network based on smart sensors that use advanced communication to control the grid, which is capable of real-time self-configuration when there are unexpected faults. Its main goal is to maintain the grid to prevent cascade effects when dealing with disturbances. To fulfill this, several requirements must be met, which are described as follows. Fault detection must be carried out quickly and accurately. The network must be reconfigured to eliminate negative impacts. The continuity of the energy supply must be guaranteed under all conditions, and failure recovery time must be minimized. The self-healing capability of the smart grid manages all power distribution equipment, including sensors for data acquisition and intelligent software systems that are responsible for analyzing, making decisions, and carrying out control actions. This is the architecture of a self-healing smart grid, comprises of control systems, real-time measurements, artificial intelligence, fault tolerant, and real-time information. And the concept of self-healing is transmission grid self-healing, distribution grid self-healing, and microgrid self-healing. Microgrids have the ability to operate in two models, island mode or grid connected mode. When in island mode, the microgrid operates as an autonomous or independent network that provides on-site power generation. Microgrids have limited capabilities, so conventional protection designed for conventional grids is not suitable for application for two microgrids. When a microgrid is connected to the main grid, the current from the microgrid is inherently much lower than the current from the main grid. Microgrid implementation on the main grid must consider protection coordination because work in any part can cause the entire system to trip, resulting in energy loss throughout the network. The difference in variations microgrids are mainly in capacity, so the protection system must be designed specifically for each microgrid. When the microgrid is disconnected from the main grid and starts in island mode, the current entering the networks and can cause significant deviations in system frequency and voltage. When the generator in the microgrid is not properly protected, this can result in a power outage. For a smooth transition between grid-connected mode and island mode, special mitigation techniques are required to ensure the reliability of the microgrid through careful design and a comprehensive understanding of the system. Load changes that exceed the microgrid capacity must be anticipated, especially during island mode, because this can disrupt network stability. Distributed generators, according to the IEEE 1547 standards, are allowed to be connected to the main grid, but when a fault occurs, they must be disconnected. Several topics that are discussed to obtain potential solutions to protection and control problems in microgrids include reciprocal power flows. The integration of distribution generators on the main grid results in a bidirectional flow, so reverse power flows are possible. Therefore, the traditional protection methods will not be able to handle the fault in the main grid. So, short circuit range limitations. The fault current in the inverter-based DGs is limited to a maximum of 2 pu. As a result, the traditional overcurrent relay is unable to detect the fault. Stability problems, the control system in the microgrid system allow local oscillations to arise. Therefore, to guarantee the stability of the microgrid, if it's necessary to carry out an analysis using the small signal stability theorem, which is answered by the transient response results. Low inertia, traditional power grids have high inertia. On the other hand, microgrids have two inertia characteristics, especially for inverter-based distributed generators. When disconnected from the main grid, serious frequency deviations may occur, so a special protection and control system is needed. Discontinuous power. Some microgrids use photovoltaic or wind or as intermittent renewable energy resources. This distributed generation produces intermittent power sources. As a consequence, there is need for a coordination between DGs and storage devices. The adaptive protection system is a protection method in which the protection related settings are adapted according to changes in network configuration using smart algorithms. Due to the immensely growing electricity network, changes in grid configuration will occur frequently. Conventional protection systems with fixed parameter settings will be unable to handle fault issues on systems with varying configurations. Adaptive protection methods that can change real-time setting parameters based on the operating state and system conditions continue to grow rapidly because they can handle fault issues even as the grid configuration changes. The use of such adaptive protection will improve the drawbacks of conventional protection systems so that it can make the protection system better. For example, enhance reliability, sensitivity, and speed of the fault handling. By using large amounts of data generated from advanced sensors, adaptive protection schemes can be developed. Stable, reliable, transparent, and easy to interpret protection algorithms are necessary to ensure the reliability of protection decisions. In addition, the protection decision must be simple, fast, reliable, consistent, selective, and sensitive to faults. To face the challenges, this section will focus on adaptive protection schemes. The growth of adaptive protection methods is rapid due to their ability to adjust the protection scheme with real-time settings based on the system operating state and system conditions. The high impedance faults produce a fault current that is relative a small consumption. When contact occurs between the conductor and a tree ground with a high impedance, it will trigger HIF. The energized fallen conductor jeopardizes public safety because of the possibility of contact with humans and the potential to cause an arc to ignite wildfires. Therefore, it's important to proactively detect and localize energized fallen conductors. According to the surveys, high impedance faults account for between 5% and 10% of overall system faults, when most faults in the electrical network endanger electrical equipment. HIFs could also have an impact on human safety and lead to legal issues. A high impedance fault occurs when an energized conductor encounters a quasi-insulating medium, such as a tree, structure, or piece of equipment, or when a fallen energized conductor touches the ground. The characteristics of HIFs are mainly determined by the materials in contact with the energized conductor, which results in different voltage current properties. So HIFs can be grouped into two classifications. The first is the active HIFs, which are usually accompanied by an arc current, and the current flowing is much less than the specified protection unit. While the second is the passive HIF, which do not cause an electric arc. Both are very dangerous and threaten the lives of people and animals because of the possibility of touching them or causing wildfires. What area protection control and monitoring is a method that utilizes synchronized measurement technology to take preventive and corrective action with the aim of avoiding the cascading effects of large disruptions. To obtain smart sensor-based data, a sensing device called a phasor measurement unit has been developed in recent years. Intelligent electronic devices implemented in the power sector, such as circuit breakers, transformers, and capacitor banks, are equipped with control and automation functions. Webcam consists of multiple subsystems, including wide area protection of control, which is further divided into system integrated protection schemes and remedial action schemes through an advanced communication infrastructure, among others. With the help of advanced sensors and a robust data infrastructures, the implementation of artificial intelligence in the protection system will provide the best solution because it can adapt it for various network configurations with high accuracy and result in a faster response than conventional protection. The protection system in a smart grid is very complicated because there are more and more microgrids and distributed generators that are sometimes connected and sometimes disconnected. To increase the reliability of the smart grid, it's crucial to perform real-time fault detection and determine their location. This allows for automatic network configuration by promptly disconnecting the faulty line segment. The protection system must be able to locate faults quickly and precisely, even as network reconfiguration occurs. The next section is the discussion. So the self-healing is a fundamental feature of basic capability that must be present in smart grid. The philosophy of self-healing capability is to increase reliability by ensuring that the supply of electricity to customer is uninterrupted. The main objective of self-healing has two functions. The first is prevention by detecting faults to ensure that customer service functions are not disrupted by hidden troubles. And the second is self-reconfiguration by restoring faults as quickly as possible. The self-healing algorithms require powerful and real-time computing systems that monitor and determine the extent of their state towards a fault state with prognostic analytic. Self-healing model is divided into 4 steps. The first step is to create a model that describes the behavior of the network. In the second step, the limits of the system status values must be determined between those that the normal and those that show symptoms of disruption, so that a safety margin model can be developed. In the third step, based on the first and second models, it's necessary to build a model of the maximum power supply recovery capacity of the normal operating feeder. Finally, based on the existing model, it's necessary to develop algorithmic steps that can be implemented to form a self-healing procedure. And the conclusion of our research is the configuration of a power grid with the integration of microgrids is a particularly challenging task because these grids are intermittent, adding complexity. And the microgrid protection requires a special methods. For example, it's necessary to design a suitable protection method for the microgrid to protect it from any disruptions that could occur in both grid connected mode and island mode. So high impedance faults are a big challenge because the fault current is relatively small compared to the network current. Advanced methods must be developed for the accurate detection of HIFs with the increasingly complex electricity network. There is a need for comprehensive coordination within the grid so that the protection, control, and monitoring can carry out their duties properly. Our conclusion from the survey results can be summarized as follows. Self-healing capability is a crucial feature of the smart grid, and finding effective procedures for it poses a significant challenge. The protection system in the smart grid is still extensive and requires further research and development. Third, the survey is expected to generate interest among both authors and readers, encouraging further research and protection system in smart grids. And here for all, thank you for your attention.